So when I switch, can you now see the PowerPoint?
Yeah.
Yes.
Okay.
Yes.
And so this is the PDF. Okay. So in this lecture, I'm going to talk about geometrical optics, and there's a bit of math involved. So usually in the past few years, I work out the math in class, but since this time I don't have that opportunity, I'm going to try my best to solve the math step by step using some PowerPoint slides that I prepared. Okay, so let's start with the lecture. So we have a brief overview of the modern view of light. I think you are all familiar with this. And if you have any questions, you can just ask me, just shout out your questions. I'll try to make this sort of a discussion as we go along. So the photon is the elementary particle of light, and it is massless and has the speed of light. Light can also be thought of as a wave, which gives us the wave-particle duality, and any wave has an energy associated with it, which is given by Planck's constant times the frequency. Can you also see my mouse cursor as I point to things? Sorry. Okay, yeah. So the momentum associated with the wave is shown by this equation. Again, so h is your Planck's constant, lambda is the wavelength of the light, and momentum is p. And finally, we have a dispersion relation, which equates the speed of light with the wavelength and the frequency. So these are just some basic definitions. And now we will look into how we can use the concept of array to solve some optical systems. So the idea behind these lectures is to get you familiarized with analyzing optical systems. Suppose you have you want to make a camera or some imaging optics, and maybe it's fairly complicated. So you would want some way of solving the math and figuring out how to build your lenses and stuff to get your imaging properties correct for your system. So eventually we will see that when optics get more complicated, like suppose even our cell phone cameras have multiple lenses these days. The DSLR cameras all have multiple lens elements inside the long tube-like lens. So for those, you would eventually need to resort to some kind of a software that is going to solve the math for you. And I think in the upcoming lectures, we have sorry, 1 or 2 tutorials which will show you how to use certain softwares which can solve geometrical optics problems. But before that, we should also understand the mathematics that goes into building these softwares, right? And that's what I'm going to talk about in this lecture. So light, as we discussed in the first slide, can be thought of as a wave. And geometric optics, what it does is it approximates the wave nature of light in the form of array. So remember, if you have a wave traveling in space, it is basically a disturbance that is propagating. So I can draw out the disturbance in the form of a sinusoid. And then suppose this is at time equals 0. So the wavelength is defined as from suppose from a peak to a peak or a trough to a trough. You're familiar with this. And we then define a wavefront as planes of constant phases. So every point on here, which is at the same phase, can be thought of as a wavefront. So imagine the point which is at the peak, or which is at the trough, or at the 0 line. So all of these are in phase. So we can approximate these as wavefronts. So now if I advance the time by a very small time segment, suppose delta t, what will happen is that the disturbance will move forward, or in this case, it's going from left to right. So it will move toward the right a little bit more. So all these points will shift, right? So you'll see all the points which were in phase sort of moved forward by an equal distance. So it is as if the wavefronts that we defined as the planes which are going through these points of same phase, the wavefronts, the parallel line, the parallel planes, they move forward or they move toward the right. So now if we trace out a line which is perpendicular and moving through these parallel wavefronts, we can call this as a ray. It basically shows you the direction in which energy is flowing when light is propagating from one point to another point in space. So if you have homogeneous medium, like there's no change in the medium properties, like suppose the light is propagating in vacuum or inside a homogeneous medium, like inside glass slab or something, light will always travel in a straight line. That's what we assume for the time being. Next, the question is what happens when light interacts with matter. So in the case of vacuum, you see that light is just undergoing rectilinear propagation. Inside some matter, some material, light will have to encounter the different atoms and molecules of the matter. So it will suffer a decrease in the speed of light. And this, the velocity which light has inside the medium, defined by V, equals the speed of light divided by the refractive index of the material. The other way of looking at refractive index is basically the scaling factor, which goes into the reduction of the speed of light inside a material, some material, when light is traveling through some material. So we can define this as the refractive index, and an example is vacuum or air has refractive index of 1. So basically that means that light is not interacting with anything and it travels at the speed of light. While glass has a refractive index of 1.5 to 1.6. Certain other materials have even higher refractive indices and so on. So which means that inside those materials, the light is basically slowing down. Next, we come to another term called the absorption coefficient. This tells us how much of the light energy will be lost by absorption by the material molecules. And that is defined as alpha. And the energy transmitted through a length L of the material is defined as, so this is basically the energy is transmitted is equal to exponential minus 2 alpha L. So just this is basically a scaling down of the energy. So some energy is absorbed inside the material. Example, so I just said glass has refractive index of 1.5. On the other hand, glass fiber has a very low absorption coefficient. So you can see the absorption coefficient is second place of decimal per kilometer. So see, the definition is with respect to a length L which is traveled inside the medium. So over really long distances, glass fiber has very low absorption coefficient, which is why optical fibers are made of glass and it can carry light for very long distances without suffering significant loss in the transmitted signal. Okay, so now we come to the two primary phenomenon associated with optical systems. The first one being reflection. So reflection, can think of reflection from any surfaces. Mirrors definitely come to mind. And I think we have all learned this equation in high school. So if you have an incident light defined as a ray coming in, let me see if I can see the chat, if any of you ask any questions.
No question.
Okay, yeah, I don't think I can see the chat. Yeah, but anyway,
No
if you have
right
questions, just shout out your questions, maybe. Yeah. So
I can monitor it up with him. It's okay.
Okay, so yeah, so if you have an incident ray of light coming in as shown over here, and the incident light is coming from a medium 1, And this line shows the interface between medium 1 and another medium, which is this medium 2. And this interface is reflective, which means most of the light will hit the surface and go back into medium 1. We can draw this ray, which I'm now pointing to, as the ray which shows the reflected light. Now we draw the normal to the interface between the two medium. And the law of reflection states that the angle subtended by the incident light with the normal, defined here as theta I, will be equal to the angle subtended by the reflected light to the normal, theta R. So simply, the angle of incidence equals the angle of reflection. Obviously, remember that in no medium is perfect, so some of the light will also get refracted into the medium. But if it's a very, very ideal reflective surface, this energy is very, very low. So, and the other law is that the normal, the incident, and the reflected rays all lie in one plane. So in this case, everything's inside the plane of the screen, basically, that we're looking at. Okay, so the second phenomenon is refraction. In this case, suppose the medium is, just a second. So suppose the medium is, the first medium is air and the second medium is glass, or the second medium is water. So in this case, most of the light will enter the second medium, but it will suffer a change in direction of propagation. But again, a small amount of energy is going to get reflected back. So in the case of refraction, we define the angle of refraction as the angle between the refracted light, which is going into the second medium, with the normal, right? I think someone has trying to enter the room. Dr. Menon, can you? I should probably. Okay, I think someone got added. Yeah. Okay. So the Snell's law defines the phenomenon of refraction, which states that the N1, which is the refractive index of the incident medium, or the medium from which light is incident, times the sine of the incident angle, theta I, equals N2, which is the refractive index of medium 2, times the angle of refraction, theta T, defined as the angle between the refracted light ray and the normal. So this is Snell's law, very important, and we'll use this multiple times going forward. And again, like in reflection, the incident, the reflected and refracted rays all lie in the same plane. So just 2 points to remember. In the case of reflection, most of the light is going back into the medium from which it was coming in. And in the case of refraction, most of the light is going into the second medium. Again, in either case, a small energy is going to be, so in the case of reflection, going to be refracted, and in the case of refraction, going to be reflected. The next case is a special case of refraction, which is called the total internal reflection. So a good way to visualize what is happening is if we look at refraction taking place, and imagine if the light incident angle is increased. So suppose this ray goes more and more towards the interface. So theta I becomes larger. What will happen is theta T will also become larger. And if you keep increasing it more and more, if you keep increasing theta I more and more, what will happen is at one point, the theta T will go along the edge of the interface, which is the critical angle, and any angles of the incident angle which is greater than the critical angle, no light will be able to enter the second medium. All of the light will be reflected back. One important point to keep in mind is this can only take place if the first medium has a refractive index which is much higher than the second medium. So one example would be when light is going from glass to air. So if you have a light going in at angles which is greater than the critical angle from glass to air, it won't be able to escape from the glass, sorry, and will get completely reflected back into the glass. So this is total internal reflection, and it's the concept which is also used in optical fibers to keep light confined nicely within the glass fibers. So remember, when theta I becomes the critical angle, the refracted ray grazes the interface. So you have theta T equals 90 degrees. And any condition where the critical angle has been exceeded, all the light will be reflected back, which is called total internal reflection. Okay. There can also be a special case called the frustrated total internal reflection, where if you have three medium, so basically actually two mediums, so it's like medium one, the incident from which the light is incident, and it's going finally into another third medium, which is equal to the refractive index of the first medium. And if you have a very thin medium sandwiched in between these two layers called medium 2, and this thickness has to be like really, really small, in the orders of a few wavelengths of the light. So the idea is that most of the light will get reflected back following total internal reflection, but some of the light energy leaks through this interface and propagates into the third medium. This is but this energy, the energy carried by this light is pretty low, and most of it is evanescent waves. But it's just an interesting phenomenon to keep in mind, I guess. Okay, so so going forward, the things that we will keep in mind is that in geometrical optics, we are dealing with systems which have dimensions which are much greater than the wavelength of light. So imagine a standard mirror is like 1 or 2 inches in diameter, but the wavelength of light is in the order of nanometers, right? So the difference in scales is huge. Wave effects such as interference and diffractions will be ignored. Again, you can also work with problems which cannot ignore these situations, where the structures that you're dealing with have dimensions close to that of the wavelength of light. Like when you're dealing with nanotechnology based systems, nano photonics and stuff like that, they have features which are in the order of microns to nanometers. So in those cases, geometrical optics is not a good as approximation, and we have to resort to wave optics. But that's not the aim of this class, so we'll ignore those. But geometric optics is very useful for everyday stuff, like big optical systems like telescopes, cameras, microscopes, and all these things. So it covers a wide range of devices that we come across every day. So geometric optics that way is a very powerful tool. And it's, yeah, so it's simple and sufficient for most situations. Okay. So going forward, any questions up till here? Okay, so the Huygens principle shows how from a point source. So if you have, so imagine this is an infinitesimally small point source from which light is emanating. So how does light propagate away from this point? So the principle states that the point source will create a primary wavefront, and on each point on the surface of this primary wavefront can be thought of as a secondary point source, which itself creates another circular wavefront. So if you then draw an arc connecting all these smaller circles, what you basically get is a bigger circle, right? So, and then on each point of this dotted curve, if you again think of as a secondary point source, you can repeat this and you'll get another circle and so on. So basically in 3D, you have a sphere which is increasing in radius, carrying energy away from the point source. And in 2D, it's a circle. So each point on a wavefront acts as a secondary point source, emanating spherical waves. And after a short propagation distance, the superposition of all the smaller spherical wavelets gives rise to a larger wavefront, which is the secondary wavefront. And you keep repeating it, and that way you can map out how the light is propagating away from this point source. Okay. So now the question is, why are imaging systems necessary in the first place? And why did we talk about this principle? So imagine you have some objects in space and light is scattering off from that object. That's how we basically see anything, right? If light scatters off that object. So once light scatters off different points on an object, it is going to create all these different small wavelets, which basically go out in space. Now, the information is being carried, the information regarding the object, the visual information is being carried by these wavelets, but in space, they are basically jumbled up. So in space, they get all jumbled up. Now you need some system which is going to take all these jumbled rays and bring them to a point which resembles the object from which they were either scattered or emanated. Otherwise, you can basically not make sense of the information which is out there in space. And making sense of the information is basically how we see something or image something. So seeing is basically with our eyes, imaging is with a camera or a telescope and so on. So the optical system, which is used to collect all the information which was sent out from the object, is an imaging system. In short, it is a lens. Like our eyes have the natural lenses of our eyes work by the same principle. So all the light which is scattered from 3D objects in space around us, they are brought to a focus on our retina by the lens. And that is how we can make sense of the world around us. So imaging systems are very important. And without them, it is not possible to image anything or make sense of the information which is carried by light from objects.